Again, welcome to today's webinar, Data Warehousing with Amazon Redshift. Our presenter today is Tony Gibbs. Tony is a member of Big Data Specialist team at AWS, where he focuses on data warehousing solutions in Amazon Redshift. Prior to joining the Big Data Specialist team, Tony worked as a software development engineer at Amazon Destinations. Tony holds a bachelor degree in computer science and economics from the University of British Columbia. Today with us we also have Annie Soon and Kasir Mujwar. They'll be our moderators today for the session, answering your questions through the Q&A panel. Tony, welcome. The floor is now yours.
Hi, thank you for joining us today for the webinar on data warehousing with Amazon Redshift. My name is Tony Gibbs and I'm a solution architect and member of our Big Data Specialist team. Today, I'll be diving into the storage system of Redshift and also the parallelism of Redshift. But for those of you who are less familiar with Redshift, I'll be covering all the needed concepts and terminology. So this is a more advanced talk, but if you haven't used Redshift before, I think you'll still get a lot out of this presentation or webinar. So we're going to start out with just the history and development of Redshift, kind of how the product came to be, and basically Redshift started out, to you it'll appear a lot like a Postgres instance. It kind of has a Postgres endpoint, and if you take that and you mix it with a columnar backend storage engine, make it massively parallel, so this is fully horizontally scalable solution, and you add a whole lot of OLAP functions like windowing functions. These are SQL OLAP functions, approximate count distincts, and other SQL functions to do analytics. That's and you wrap all of this within the AWS infrastructure. That's kind of a lot of what Redshift is. Now, within the AWS infrastructure, we use simple workflow behind the scenes with Redshift. Redshift also lives within VPC, typically. It supports IAM for loading and unloading of data from S3. Redshift is also built on top of EC2, and we typically load data from Amazon S3. Data is loaded and unloaded both from S3. Redshift also supports full database encryption, and to help manage this, we use our key management system or service, which you can do to hold, the encryption keys and such. We also use Route 53, which is our DNS service for connecting to the endpoint. And we surface a ton of metrics, CPU, network bandwidth, and that sort of thing into our CloudWatch. And it really is kind of the combination of all of these components that make Amazon Redshift. Amazon Redshift was launched in February 2013, was when it went live. And through that time, over the last 3 years, 9 months or so, we have innovated like crazy. We've released more than 100 patches, and these are significant patches. Over that time, we typically do releases every 2 weeks to Redshift. And through that time, we've released 130 significant features. These are features like our Python scalar UDFs, alter table append, for example, and a ton of performance improvements along the way. So since its release up until now, Redshift has just gotten bigger and better. So I'm going to go into the Redshift cluster architecture. This should be where, if you haven't used Redshift before, I think you'll find this quite helpful. As I mentioned, the Redshift is it has this Postgres front end, and that's what on the screen here what you're looking at, the leader node. You'll connect to that with, the SQL tools like JDBC, ODBC, or other Postgres compatible drivers, and you can talk to the leader node with that. Behind the leader node, we have what are called compute nodes, and you'd have 2 or more of these. compute nodes. And this is the part where the data is stored on disk, where queries execute, and they all execute in parallel. And then these compute nodes can talk to other services, such as S3, for example, where we can load data, do backups and restores, and that sort of thing. All of this, which is Redshift here, this all lives within one of your availability zones. So we're going to jump more into the compute and leader node components. And we're going to start out here by talking about the leader node. Now on the leader node, this is where, this is what you connect to with your SQL endpoint. And the leader node does parsing and query rewriting, the planner lives there. We compile the queries down to C++ code and we send that down to the compute nodes, which we'll get into. Other bits that are there that would be familiar if you use Postgres, for example, the Postgres catalog tables live on the leader node, so you can query those as well. Our workload management system and task scheduler also live on the leader node. We won't be getting into those in this webinar. So kind of focusing a little bit more on the leader node, like I mentioned, this coordinates things like our replication process. It does, it coordinates the backup and restore processes. But the bits that we're going to really focus on are these ones for this webinar. We're going to focus on how data is stored in Redshift, how disks and slices and tables are all structured. And that's what we're really going to focus on. So in order to build up for that, we're going to start with some concepts and terminology. The first one is that Redshift is a columnar store data warehouse. So what this means is that data is stored on disk column by column rather than row by row. This gives the advantage of, say, for example, if you're only wanting to query a subset of your columns, in that we don't need to read all of the data. We only need to read just the data for that particular column. An example would be, if you were only wanting to select, in this case, this date-time column, for example. We only need to scan that data off disk. So the point here is that we're trying to reduce the amount of I/O that we have to do. The next bit is data compression. In Redshift, we support a whole bunch of various data compression types. If you look on your screen on the create table syntax there in the top right, you'll see that there's these encode keywords there and various types of encoding types that essentially compress the data. Again, the goal here is to further reduce the amount of I/O we do. The other advantage is because Redshift is a columnar store, we see on average about a 3 times compression. One of the reasons why is because, say for example, if the data is stored by its data type on disk, we would see better compression than if it was stored row by row. The next part that we do in Redshift to help reduce I/O is something that we call zone maps. Zone maps are basically an in-memory data structure that hold the min and the max values for each of these blocks, as we call them, which we'll get into further in this webinar. These blocks storing the min and the max value for each of these blocks allow us to effectively prune and filter data. And again, the goal is to reduce unnecessary I/O. I'm going to go into an example of how these zone maps work here. Say for example we have some column, and this column has a whole bunch of it's storing, in this case, date times, for example, and it's just randomly kind of stored. And if you end up coming along with, say, like a SQL statement that looks something like this, what we can do is we can check this in-memory data structure very quickly, and we can determine which blocks on disk we need to read. So in this particular case, we can reduce, the I/O, and we only need to do, by 25%. If, for example, though, we sorted the data, so we sorted these date times, the data is all sorted on the table by these date time column, and we run that same query against this. That makes the zone map significantly more effective. In this particular case, we know exactly what block we want to read off disk, and we only read just that block. So again, the kind of the theme here is what we try to reduce I/O as much as we can in Redshift to improve performance. So the goals of sorting really are about making, the primary goal for sorting is really to make these zone maps very effective. It's ordering the data of the table by a certain column, and it allows us to reduce the I/O, especially when you're doing range-restricted scans, like if you're doing like a timestamp and you're filtering between a handful of values. The next piece that we're going to jump into here is slices. This is kind of a terminology thing. You can think of a slice as a virtual compute node. So when we were looking at that previous diagram, architecture diagram with the leader node and all of the compute nodes, you can almost think of these as a virtual compute node. In that what we do is we take one of our nodes and we split it up into either 2, 16, or 32 slices. And we store the data slice by slice, and each slice basically has its own kind of set of resources, its own memory and CPUs, and they work independently from each other. So that's how we're able to achieve such parallelism in Redshift. That kind of leads on to distributing of the data. So how does the data get distributed in Redshift across these slices? Well, we have a few different techniques for that. The first one is something we call them distribution styles. And the first distribution style I'm going to talk about is called key. So this is essentially where you pick a certain column in your table, and we hash that value and kind of do like a modulo operator on it, and that's how the data gets split across the cluster. So you want to pick something, it's nice high cardinality, that's going to result in a nice even spread of data. The next distribution style that we have is something that we call distribution style all. This creates an entire copy of a table on each node in your cluster. This is used typically for, say, smaller dimension tables. This is, you might have like a fact table and some dimension tables around it. And so this is where you would use distribution style all on those smaller tables. If none of those distribution styles work, we also have what's called distribution style even, which really just round robins the data. I'm going to go into some examples here about this just to kind of illustrate. On the top left there you can see the create table syntax. So the distribution style is really just kind of an extension of that. So you'd say at the end of your create table, dist style even key or all. If you don't specify this, it'll default to even. And in this example, let's pretend we have some data that we're going to insert. We have these 4 rows here, and we're going to just distribute them by even here to start. So in this particular case, the data is just going to be simply just evenly distributed across the cluster, basically like that. It's not looking at any of the columns, it's just going to continue to do that. If, for example, though, we went with distribution key, and we picked a key such as the location there. So in this particular example, if you look in the insert statement there, the location is SFO, JFK, SFO, and JFK. So in this particular example, what's going to end up happening is the data in your Redshift cluster is probably going to land something like this. Now, this is actually an example of picking a distribution key that isn't very effective. And the reason why is the data in this example has only landed on one of your compute nodes. You have 2 compute nodes in this example. And so what would happen is if you sent a query to this Redshift cluster, only one of your nodes would be working on this query, which means that half your resources are going unused. So what if we picked a better distribution key? So in this example, I picked this AID, which I guess is our audience ID. And now this is, integers. They're 1, 2, 3, 4. So if we were to hash these, we could hope that maybe the data would land something like this. And it would result in a nice even spread of data across the cluster. So moving on to distribution style all, how this works is we if we start distributing the data, you'll see that all of the data is written to each node. So we actually put the data onto the first slice of each node. And then the goal here is to minimize network broadcasts. So if you were doing a join between tables, all of the data would be on each node, and we don't have to broadcast any data across the network doing a join. So just kind of to recap on data distribution and kind of how this works. You'd want to use key when you can create an even distribution of data using a particular column. Particularly when you can use that to optimize a join, say between two large fact tables. If you had, like, for example, one fact table with 1 billion rows, another with like 10, and you wanted to join this, and you could create a nice even distribution of data by using that key. This would be perfect for that. You would want to move on to using distribution style all, like I said, on your small and medium-sized dimension tables. We define small and medium dimension tables as basically being less than 2 or 3 million rows. And if neither of the other two apply, then you'd want to use distribution style even, basically round robin the data across your cluster. So that kind of leads into our storage system. So our Redshift storage, one of the things that I don't know if this is in the documentation, but we actually have, the disks are 2.5 to 3 times bigger than the advertised storage capacity. So for example, if you took like our DS2, the DS2 instance has 2 terabytes, for example. Redshift actually has 6 terabytes in that example of storage space. The space that we advertise for you is 2, and that's the user space. The reason we do this is because we actually split the drive up into 2 partitions, and we store 2 copies of the data. One is the local storage that can be accessed by the local compute node, and the other can be accessed by a remote compute node. And we store a mirrored copy of the data for just durability and safety. These partitions, they're raw devices, and these are local ephemeral storage. So in the EC2 world, we call this the ephemeral storage. And they basically, we have multiple disks on each of the compute nodes, and this is done for fault tolerance and failure as well. All of the blocks, which I've kind of hinted at, we haven't really got into this much yet. So the data is stored in Redshift in these 1 meg chunks, and these are per column, and we call these blocks. And as I mentioned, we store for each of them the zone maps, which hold the min and the max value in memory. These blocks can be compressed. We have 10 different encoding types that you can pick between. We also have some tools to help you pick compression, which I'll get into. Each column in Redshift is comprised of what we call a blockchain. There's actually can be up to 2 blockchains. A blockchain is really just a list of blocks. You can think of it like a doubly linked list where you have one blockchain for the sorted region and one blockchain for the unsorted region. And how that works is if you're say adding data to Redshift, and we talked a little bit about sorting earlier. The sorted area is one blockchain. Then we kind of keep track of the unsorted data in a second blockchain. And then when a vacuum comes along and kind of resorts all this data, that would merge the blockchains together. We also have 3 columns in Redshift that are hidden columns. You can't query these, but you will see them in some of the system tables when you're querying, and we have this in Redshift for multi-version concurrency control. So Redshift, it's transactional database, and it supports MVCC. So these 3 columns, one would be the row ID, one would be the deleted ID, and one's the transaction ID. So Redshift is designed around large batches of data. So it's a petabyte scale data warehouse, and it's not, so it's designed around loading, hundreds of thousands or tens of millions of rows in a single shot. So that's the typical use case for it. It doesn't do well with small writes, like this would be an insert statement. For example, 1 row, 10 rows, whatever. Those are fine if you're just doing, development, testing stuff. I insert data all the time in small little batches just for myself. But typically you want to be loading in production, especially loading data using the copy command in large chunks. Now the reason why is these 1 meg blocks in Redshift, they're immutable. So say, for example, you come along and you just do an insert statement. What we do is we pick up the last block in the blockchain, we clone it, and we add your row to it, and then we write it back to disk. The reason we do this is we don't want to introduce any fragmentation in the blocks and basically have like half written or just tiny blocks that are 1 meg that only contain a small bit of data. Deletes in Redshift, we essentially mark the row as deleted. So we just go along and we tag the rows as deleted. The space isn't reclaimed until vacuum operation comes along and reclaims that space. Updates, they work, they essentially delete the data and insert it to the end of the table. So as I talked about earlier, compression. We have a couple of ways that you can compress data easily in an automated way. One is if you don't have any compression settings set to a table and you do a reasonably large copy statement into that table, we will automatically figure out the compression for you. Optionally, you can also use a command we call analyze compression. So you type out analyze compression in the name of some table, and we'll sample out a bunch of data out of that table, and we'll compress it with all of our different compression algorithms and figure out the optimal compression setting. If you, say, want to use analyze compression in that way, and you figure out the various compression settings that you want, what you'd end up doing is you'd end up recreating a new table and copying the data from your previous table into the new one. Distribution and sort keys, those are probably the 2 most important in that order. To make sure you get right when you're working with Redshift, they significantly influence the performance more than any other. And then the next would be compression. So we're going to jump into the parallelism part of this webinar. And just to kind of recap on slices, yes, they're the virtual compute nodes essentially in Redshift, and they are how the data is distributed. So a little bit talking a bit further on this, we're going to actually focus on the stuff on the top left here, the parser, the rewriter, the planner. So this section right here. Basically, when a query comes to Redshift, we parse it. We actually will rewrite the query. This kind of strips out some of the syntactic sugar that's in the SQL language. We'll then run it through our planner, which is going to generate a whole bunch of different plans. Our optimizer will look at the statistics in the database and pick the optimal plan. Once it has that optimal plan, it passes it through to our code generator, which will actually compile the code down to C++, into actually multiple C++ functions in many cases, and it will send that compiled code down to the compute nodes where they'll execute this query all in parallel. There is one actually little bit there, and this may be for those of you who have used Redshift before in the past. Before we generate the code, we'll actually check a cache, and we'll actually cache some of those compiled that compiled code, and if we don't need to compile the code again, we will reuse it. So that's in one of the cases where if you've used Redshift, you'll notice that the second query run is in a lot of cases faster, and that's because you're skipping that compilation step the second time. So we're going to talk a little bit about the terminology, and I'm going to start from the bottom here and talk about a stream. So you can think of a stream as, at a high level, you could almost think of it like a reasonably small query. Maybe, for example, you may have your query could consist of more than one stream. One easy way to kind of conceptualize this would be, imagine you had a query that maybe had a subquery in it, for example. That subquery may end up being one stream. The output of that query would feed into, the query that's above the subquery. Each of these streams is broken up into segments. So these segments can all execute in parallel. These are the individual C++ programs I kind of talked about, or functions. And so all of these segments can run in parallel. Each segment is built up of a handful of steps. These are kind of, they have to, you move from one step to another, and that's what builds a segment. So kind of just to illustrate this visually, this could be some example of a query that is comprised of 3 streams that consists of a handful of segments each, and each of these segments obviously has a handful of steps. So you can't proceed on to the next stream until the previous stream has finished. So this kind of leads into the life cycle of a query and how queries work in Redshift. So imagine you come along with whatever your favorite SQL client is. Maybe it's using JDBC, ODBC, or as I said before, any other, or some libpq client. And you connect to the leader node and issue some query. As I mentioned, the parser is going to pick that up. The query planner is then going to, take the query, the rewritten query, and it's going to generate some plans, passing it off to the optimizer. We're then going to, from there, generate some code, which is going to consist of a handful of segments for one stream. That code gets passed down to the compute nodes. The compute nodes are then going to run that code, picking up whatever data they need to do and kind of figuring out the results. And those are going to get sent back up to the code generator. So what's going to happen here in this particular case is we're going to generate a new stream, which is then going to send back down to the compute nodes for the second stream, and they're going to then run that code, send back up. There's no more streams in this particular case, so we're just going to send those results back up to the leader node. Now the leader node at this point is going to have to do some last computations. This might include, like, if you had an order by, for example, in your query, or any final summations or counts or those sorts of things. This final result is then going to be sent back up to the client. So I'm not going to talk about this slide or this slide. That's basically a repeat of what I was just explaining while walking through the life cycle of a query. But if you, after the webinar, if you want to download these slides, you can read through these sections, and it's a repeat of what I just said. So as we had before, these streams and segments and all of this, the important concept here is that all of this happens in parallel in Redshift. So if we, for example, had a small little 2-node cluster, each comprised of 2 slices, in that particular example, all of this would be happening in parallel on each of the slices. So moving on with parallelization in Redshift, I'm going to talk a little bit about loading of data and how it happens in parallel. So in this particular example, we have a single node cluster, and we have some single file that we want to load up using the copy statement in Redshift. In this particular example, what would end up happening is the copy statement would reach out to S3, pull up this file, and what would end up happening is one slice in your cluster would be downloading this file, parsing it, and basically having to redistribute it across the cluster and write it. This isn't very efficient in Redshift, and the reason why is because you're really only using one of the slices in the cluster. So how to optimize this is imagine we split this file up into 16 chunks in this particular case. So if you were to do this, what would end up happening is the leader node would basically reach out to S3 and figure out, okay, I have 16 files, and it would ask each slice in parallel to download and parse and distribute that data and all write it to disk in parallel. And this scales linearly So in this particular case, you would see at least a 16 times performance improvement, actually probably a little bit more. So we have a handful of open source tools, which I'll quickly talk about on our GitHub, on the we call them AWS Redshift utils. For example, those are some of them, but these are all on our AWS labs on GitHub. The Redshift utils, it kind of consists of a bunch of admin scripts and admin views where they're queries that we've written that we find helpful for just kind of looking some of this information up. Maybe if you're wanting to, look at, for example, like we have the loading query, like for example, the query reports and those sorts of things for looking at segments and such. You can find information on there. We also have our column encoding utility, which can help you migrate tables. If you had a table that wasn't compressed as optimally as you would like, and you wanted to migrate that, that utility can help with that as well. So I think I'm going to open the floor here to Q&A. That's the end of this webinar, but we have some time for Q&A. Thank you, guys.
All right, and thank you. Thanks for the great presentation today. And we'd like to move on over to our Q&A session. You notice we have our polls open in the bottom part of the screen, and that's where you can go ahead and fill out your responses, your feedback. It's very important to us as we go through the Q&A here, so please feel free to fill those out. If you have more questions, you can put them in the Q&A panel in the upper left corner. And we have Annie and Casey here, and Tony will answer our Q&A questions.
I'm going to start with one question here that just came in. How and when are patches applied to Redshift? Patches are applied in Redshift in your maintenance window. So when you create a Redshift cluster, it can actually be modified also later after the fact. We will, within that maintenance window, it's a 30-minute window that you set, we will do the patches at that time. Technically the window is every week, but we usually only apply a patch every 2 weeks. So that's when the patches are done. The next question is, how much do backups cost in Redshift? And are they billed at S3 rates? No, Redshift is all-inclusive. So the backups are actually included in Redshift. So yeah, you don't actually pay for the backups. They're just simply included. The next question is if we define sort key, we have to groom manually or automatically sort after a load operation. So when you load data into Redshift, there's 2 steps with the copy. The first step is we do what's called a local sort. So the data will be sorted locally within that copy, but the data will still land on the unsorted blockchain. There is a maintenance task that we call vacuum that is, a lot of customers will run, say, nightly, others will run weekly. It depends on the frequency that you load data, and that will essentially merge the blockchains together and do what we call a global sort. But the data will continually be locally sorted, which helps keep the zone maps still in good shape. Eventually, you'll obviously need to do a global sort, though. The next question is, can one access the compiled query or write it in compiled form? There isn't a way really to access the compiled query or write it in compiled form. So yeah, unfortunately we don't expose that. Aside from testing different disk styles with the same data, are there tools available to analyze which distribution styles yield the best performance for your use case? There aren't any tools for this, but I'll kind of recap that the most important thing is to make sure that there's an even spread of data. We surface the it's called data skew, and it's surfaced in a table called SVV underscore table underscore info, and that's the best place. That's like where you should look for, and make sure you get that even distribution of data. After that, it's about the next, most common way to make sure that to get the most performance out of a distribution key would be for optimizing for joins. The easiest way to do that is if the smaller tables are all distribution style all. If you have larger tables than that, then that's where you need to make sure you can distribute on the same key for them. That's really kind of the rules of thumb. So they're usually not as tricky to figure out as sort keys, which sometimes is where you need to do a little bit more experimentation to make sure you get those right. The next question is what is a typical DR plan or disaster recovery? So Redshift, as I mentioned, we do store redundant copies of the data in Redshift. That's where we mirror the copy to another node. The next bit is that we're constantly backing the data up. I know I kind of mentioned backups in kind of what we were going through here very quickly. So how backups work in Redshift is there's an asynchronous process that's always synchronizing data from the compute nodes to S3. That process kicks off whenever 5 gigs of data in Redshift has changed, or 8 hours, whichever happens first. So in certain cases, it can pretty much always be running. You can always restore that backup from S3, which is very durable storage. The other option is that we also support what are called cross-region replication on those snapshots. So you can replicate those snapshots from one region to another. So an example, you have a Redshift cluster running in, we'll say, US East 1, and you could enable a snapshot of your cluster to be continuously synchronizing and backed up to US West 1, where you can then restore that cluster. The next question is, do we need huge amounts of bandwidth to transmit the data from internal systems like our systems and hard drives cloud to the limit? Well, you need as much bandwidth, I guess, as necessary to send whatever you're going to be loading into Redshift. We highly recommend compressing the data before sending it to S3, which is where you would end up sending it. So one of the things is those files, in the last part of the webinar there, which I was talking about, you'd want to split the files up into chunks. We typically recommend those chunks to be somewhere between 1 meg and 1 gig after compression. So one of the important things, though, is that Redshift does support loading, for example, gzip compressed data, which is what we would recommend doing to greatly reduce the data that you're sending. The next question is are there additional steps that need to be taken on data before running the parallel copy? This kind of falls in line with a little bit with the last question and the answer that I had there. Really the biggest step is to make sure to gzip compress the data. And like I said, the chunk sizes that we recommend are 1 meg to 1 gig. If the file size is less than 1 meg, like for example, if it's just a really small load, it doesn't do anything bad. It's just it's not as good for performance. So yeah, just somewhere in that file range is ideal. The other thing is the slices that you have in the cluster. You should have, if you can, obviously in the example we had an exact even number of files as we had slices. The number of files can be some divisible number of that. So in that case, we had 16 slices, 16 files. You could load 32 files or 48 files or whatever makes sense for you. After copying data to Redshift, how do you transform the data? A lot of people will, for example, load the data into a staging table. It's really common. So they would end up issuing a copy statement into a staging table. And then they would then, query the data out of that staging table, doing any transforms from that into the production table. It's very typical to do, for example, deduplication of data, where maybe you're restating data. And in that scenario, what you would end up doing is, say if you had your staging table and some production table, is you might issue all in a transaction, of course, you issue your copy. You would then delete the data out of the production table and then do a complete move or copy of the data along with whatever transforms you need to do from the staging into the production table. Does Redshift support full Postgres? Views, indexes, stored procedures. How does one know the differences between Postgres and Redshift behavior? So we've documented this quite a bit. I think there's 3 or 4 different pages in the documentation, which you can search for if you search for something like Redshift, Postgres in our docs. You will find the differences. Most of the functions in Postgres are in Redshift. We've also, like I mentioned, added a lot. Views are in Redshift as well. Indexes, for example, they don't really apply to Redshift, so they're not actually in Redshift because we obviously use sorting and distribution for performance. And we do not have stored procedures, but we do have user-defined functions that can be written in Python, and these are user-defined scalar functions. Next question is what are some of the resources to look at for performance tuning? One of the best ones that I recommend quite a bit is to look at, it's our top 10 best practices blog on the AWS Big Data blog, and it's written by Ian Myers. I would search for that blog. It kind of covers kind of like the top 10 things that we see that that just people get wrong, or things that maybe could be optimized slightly. So I would definitely look up that blog and follow the guidance in there. It's a very good blog post. The next is are unique constraints part of Redshift, and what happens when a file contains invalid data or there is an error inserting from S3? This is kind of a bit of 2 parts here. So the first is I'll talk a little bit about constraints. So unique constraints, you can declare them in Redshift as well as primary keys and foreign keys. However, they're not enforced by Redshift. I still recommend declaring all of these if you have a foreign key or a key that should be unique. And the reason why is that the Redshift optimizer, when picking a plan, will look at these constraints, and it will assume that the data is unique or that a foreign key applies. And it can help with performance just by picking the correct plan. The next bit is when loading data, so you won't get a copy error, I guess, when you're loading data from S3 in this particular case on a unique constraint, for example. That's where you would end up, in a lot of cases, loading into a staging table, it may make sense, and deleting data or deduping your data in some way. If you have large batches of data that you needed to, for example, that you loaded into a staging table, I'll just kind of mention one of the features that a lot of people find useful and very fast is we have a feature called alter table append in Redshift. It was added last February, March of this year. And what it is it's essentially like a move operation, and it's very useful on moving large chunks of data. So if you ended up having like 100 million rows that you wanted to move from a staging table into a production table, that's an excellent use case for this alter table append feature that we added. For smaller chunks of data, it just makes sense just to simply do an insert select. The next question is do I have to actively manage the cluster, making changes to increase performance, index recommendations, or does AWS provide smart recommendations based on query performance? So within the cluster, that is something that that you, the customer, have to manage. We take care of all of the maintenance of the particular cluster. So this is, obviously, like I mentioned, the patches, the operating system, all of these sorts of things, the disks and all of that stuff is all taken care of by AWS. The parts that are inside your cluster is up to you to take care of. And some of the GitHub utilities that I was mentioning at the end of the webinar there, in the admin views and in the admin scripts, that's where you'll find a lot of that information. So, for example, a couple of the admin scripts we have, they're called performance alerts, for example. You might want to take a look at that, and that'll give tips, like, for example, on maybe you scanned a whole bunch of deleted rows on a query, or you have queries that are not using something like data that's that you've sorted by, for example. So if, say, you're constantly filtering on data that isn't part of any sort key, it would raise alerts like that. And that's why we've added this GitHub utils site, is to help with that. The next part is Upsert going to be part of Redshift? We're always constantly taking feedback from customers. That's something that people ask for. So yeah, thank you very much for the continued feedback. I noticed there was just another question I see here on merge statements, which are essentially the same thing as an upsert, and we're always taking customer feedback. So thank you for that feedback. Thank you guys very much this afternoon for coming out and listening to our data warehousing on Redshift.
A special thank you here for our presenter Tony today for his time and the great presentation we had today, and I'd like to also thank Annie and Kansir for answering our audience's questions through the Q&A panel. If you have any comments of our previous or upcoming webinars, or any suggestions on the topics that you wish AWS to cover in future webinars, please feel free to email us at aws-webcasts@amazon.com. Your feedback will help us improve our webinar programming. Thank you to the audience today for taking the time with us. Everyone, have a great day, and you can disconnect at this time.